大家好，我是王不老说半岛。Hi folks, today I'm going to continue my packaging process technology talk with a focus on organic interposers as requested by someone. And and would like to answer this question: where organic interposer eat silicon interposers lunch? And then I would like to show you how Bin can help me to explore some of the topics of interest. And this is the page we presented last time, which I used Perplexity AI to generate a table to compare three interposer materials, silicon, organic, and glass. And you can clearly see that the number one reason people go with organic is cheap. It's much cheaper than the silicon by 1 to 2 order of magnitude. The limitations are their thermal and mechanical properties. Uh, they are pretty much organic material. You can imagine that. They have less rigidity and they have probably a poor thermal expansion. So why organic interposer then? The first is the cost. A silicone interposer will give you it give you very high performance in a very small package, but it costs like $30 to $100. Depends on what technology you're going to use. And in contrast, organic interposer only going to cost you $2 to $3. So this is a 1 to 2 order magnitude difference. Hence the reason why people would like to see whether the organic interposer OI, as I said here, can somehow break into silicon interposers market. Because cost of shrinking, as we explained in the last talk, is skyrocketing. So that's the chiplets coming into play. Nobody can build keep building a bigger and bigger die with a lower yield and then at a more and more advanced node. So just pack it together by assembly the relevant dies together. You get similar functionality, and that's the intent. And it turns out that people believe that OI is getting there. It's getting good progress in terms of warpage, which I doubt, but that's what people say. And then they have a very high flexibility to attach other dyes. We can imagine the organic interposer just like epoxies. And then you could pretty much, if you could you could put your process technology on a piece of epoxies, epoxy, then you could do a lot of things. And people also believe that organic interposer closing in silicon interposer in density like 2 by 2, right? The line spacing, they could do 2 by 2 now. So it's getting much better than before because you could throw a lot of money in GD and try to improve the material process of the OI that you're going to use. Later, we're going to introduce a very key OI player in our talk. Before we do that, let's look at this table. This table by Usman is interesting. The good, the bad, and the ugly of the three interposers materials. And you can see that the mechanical and thermal is probably the weakest link of organic material. This is the ugly one. The rest, kind of okay. And where they stand out is the cost. The cost. Glass is right between. Organic is 1 or 2 order magnitude, 1 or 2 magnitude in cost much less than silicon interposers. Let's use. I would like to introduce a very interesting Elian startup. This is a startup that claimed they could get rid of silicon interposer with organic substrate, organic interposers. Okay, only it's just organic substrate, and they could say my routing can remove this. All right, they have their own proprietary routing scheme. They call it NewLink. And then because the founder has a bunch of wires Say, I only need organic substrate. I could remove the silicon interposers by a special routing they have, this new called new link here. And they could still run a similar bump stack that this one. So this is this according to what they say, right? That their approach can complete eliminate the silicon interposer, and they just use organic substrate. They don't need interposer anymore. So they could use this as their own organic interposer, right? So that's what they claim, and I'm not trying to advertise them. For here, I'm just saying that that's the claim. They could go with organic cheap packaging only without going to silicon interposers. Okay, we're not going to go to detail about this company, but there's a couple of things that just of interest. They could make it bigger by connecting more GPU with gearbox. They could connect more HBM. They have they claim it 4x more because the way they package it, you could go stack them up. I mean, that's what the what we mentioned earlier, right? They have the attach other die due to their flexibility. It's epoxy. If you do it right, if you can avoid the reliability issue of the OI, then you could imagine you could really do a lot of stuff. So that's pretty much what they claim. With their special routing IP, they could add more HBM into the same big chiplet. So that's the advantage. And then they actually went ahead and do a first silicon demo with TSMC's 5 nanometer process technology. It's recently announced it. Okay, and so this is the end result. They stacked them. This is a piece of organic substrate they used, and then they claim, of course, the performance-wise, pretty nice, meeting their spec. But I don't see any yield data. Okay, so let's keep that in mind. Well, startup always give you the good news, right? They will never report any bad news. That's understandable. And they call themselves the ultimate chiplet interconnect. So here I would like to introduce something maybe of interest to you is use Bing to explore more information. So I got interested in this one. So, so I got interested in Elion, this company. So wow, you could use the TSMC 5 nanometer to prove that their idea are good. They do a multi-die, and then the performance is very nice. And so I want to explore more. And of course, you click the link using Microsoft Bing, and this is what you're going to have. All right. So I come into Alliance website, and this is what I see. This is what we can see here. He has all these great results obtained, and I'd like to explore more about this company. So on the top right side is a bin. So you click that, and this is you come up with a conversation box. So ask me anything. Okay. And here I'm interested in the this guy, the CEO. And he's the one that has many patents on this subject. So I say, and I would ask, stymie the patent done by the gentleman, Ramin. So you start a conversation with me, and then it will give you, he will perform a pattern search on the right side panel. And wow, so this is the result. Okay. And of course, you click that, this you will find what's the relevant one. It's a bit like Perplexity AI, but it seemed to me it withdraw a little bit less information, but that's okay. it's a good start because um, the benefit of using bin here is you could chat, right? You could chat directly. Uh, you could even ask a summary about this page, this web page that's that relevant to this bin. He will try to explain to you, help you to do that. Okay, so I give you all these interesting questions. So then come back to here. I asked that question, but actually he replied with the wrong one. All right, that's the funny thing is that the one I click it, it didn't exist. All right, I scored it in before asking again to redo it. I say, no, that's wrong. And this is it reply. So I apologize for the confusion. And then, so this is what I'm looking for. All right. So, and then here's a link of this help. When I go into, yeah, it is correct. Right. So, and then Ramin's pattern is here. And if you look into his pattern, it's about some routing, some smart routing that he performs. It's not material related. Initially, I thought maybe he had a new idea about some organic OI that just performed better than silicon interposing. But that's not the case. It's just a very smart routing, so as that they could use a cheap stuff uh, that that can as a cheap stuff and can have performance matching or better than the silicon interposers. Okay, so that's the idea. And well, then let's come back to here and want to do is that the how how are the reliability? That's the thing that coming to your mind, right? What is the reliability of AR OI versus SI, the organic interposer versus silicon interposers? Well, TSMC did a good job in comparing it. So in this paper, in 2021 ECTC paper, they did do a very good comparison, side by side, that everything else remained the same. That only thing changed is the interposer material that changed from organic to inorganic. I mean, silicon. Everything else remained the same. And then the key difference is TSV versus copper via in polymer. The concern is that, well, are you going to have a better or at least equivalent reliability performance? So that remains to be seen. Okay. And when you talk about reliability test, there are three tests of interest: thermal cycle, and then this unbiased haste. So all these temperature and stress and humidity. I'm sorry, temperature and humidity. Like 135 degree humidity, 135. All these are tabulated in the JDAC. So if you are interested in performing some tests, you better follow the semi rule. And then the HTS, high temperature storage test. All these tests are outlined in the spec. And so the result is that, yeah, that they are kind of equivalent. They're kind of equivalent. Everything it did pass, and then with reasonable thermal cycle, right? So STS 1,000 hour, no problem, all pass. So, and the conclusion of the paper is that the organic interposer can be extended to 2x the radical size. That's what they claim they could do. And that's a good advantage. But remember, TSMC says 6x. If you make him bigger and bigger, this baby bigger and bigger, you could do 2x a radical size, but eventually they want to do 6x. So very large. Can the rigidity and the thermal performance of this material good enough? That's a good question, right? So I bring you this page. We discuss that eventually the cold wall solution with 6x radical size, 5,000 millimeters square RDO interposers, can do 12 stack. But But this guy say I could do well more than 12, right? I mean, the alliance say, yeah, I could do 12, but yeah, that's what they claim. But I don't have any yield data to show that we're doing the same thing. But at the end of the day, can OI penetrate silicon market? Because the market leader in this high performance computing is basically still silicon. If you could really, because that's where the money is, right? Then so you come up with a new product, a new link, all combined with organic substrate. If you can prove yourself, you don't need these fancy silicon interposers. You got a very good selling point. Okay. But whether you're going to be good for future scalability, that remains to be seen. Okay. That's probably these guys are working hard on it. But there's one thing I think I'm not 100% sure about the OI applicability into silicon interposers, especially in cooling. When the extreme scaling, when you go smaller, this thing get heat up. And basically, you need to cool the chip and the silicon interposer. And so what TSMC did, they is to try to demonstrate whether that kind of work. So it's a micro heat sink here. The water coming in takes this micro bomb going through water going through here. That's a very interesting approach. And then this been forecast in 2017. This is the logic die, right? Heat up so bad. Memory, you don't really worry about that. Memory is just memory, right? They don't have a huge dry current that heat up the die. The logic die is the one that's going to cool it off. So if you look at the recent paper done by TSMC, they're using silicon interposer, right? This silicon interposer here, micro pillars. This is water coming in and out, or water in, going out. And then they have a two special design. One is covered, one is directly contact, all right? So there are two approach. The lidded and then these direct cooling. With the lid and then with the direct cooling. Both have their advantage and disadvantage. But that's what they demonstrate. They create a micro pillar by etching into a silicon lid and force the water to go through where they want, right? That's how you arrange this micro lid. Okay. That this thing you could do easily with silicon process technology because everything is well controlled. But whether you can do that for I don't think they tested. It would be very interesting to see because when you want to say, OI going to break into a scale node technology, I need to make sure that everything is good. I may be routing is good, everything is good, but can you really scale to apply this water cooling process technology? Because things can heat up, right? And imagine a high temperature die in organic interposer. That will create more problem because fundamentally it's not that good thermal conductivity. Then there's a lot of work to be done. So my question is that, can this be done in OI, organic interposers? Okay. And recently they already did silicon interposers with a special different materials. This one they probably did with a different, they call the POR SPT. It's a special substrate, a special organic. I don't want to call it interposer, but you could imagine that it's an organic substrate. They use it and to and they improve pretty much. This silicon on insulate silicon on SOIS, this new process, they if you replace SPT GL102, which is an ABF material, a special epoxy that they use. With the new one, they didn't announce what it is. Okay, and then it got improved. in terms of the material property. It's still organic, something new. That my sense is that it's still something new, a better organic material. Uh, and then this is what they have. Okay. So this is final these infos with organic RTL, and then with this idea is a proposed SOIS structure from TSMC. It got everything better, of course. That's our point, right? And SPT here, I would like to introduce this organic stuff. It's called it's ABF GL102. This material, I think it was the PR material, and then they come up with some new stuff which they did not review, and that make them I would say much better, right? That the loss and then the area, everything gets scaled down, and then the pass size smaller. So that's the purpose of SOIS. Right? S is means that the silicon. Then the ABF is from Ajinomoto, this company. This company is called Ewell. The slogan, the mission statement of this company is eat well and live well. This is a very interesting company. I would like to introduce you with a small icebreaker. Okay. It's a company that makes MSG. They invented it. All right. That's the chemical company that make the MSG that we eat on a daily basis. Yes. If you eat chips, all right, you can see that in the back of a chip, they always have MSG. So, and they say eat well and live well. That's their motto per se. Okay. And this company, they come out with a new, they're pretty good at chemistry. Japan semiconductor company are very good at chemistries, producing raw material applicable to semiconductor company like HF, like auto resist. All these are just different type of either chemicals or organic chemicals. They've done a very good job in making the highest purity you could find that can be applied to semiconductor industry. So therefore, they're dominant in semiconductor process from the material and chemistry supply perspective, besides Germany. Then this is ABF applications. This is called Ajinomoto build-up material. So that's what they meant. What they can do is to create these packaging layers, fancy packaging layers. Okay, layer like these are copper, and they could do it easily. Right? Let's look at their process flow. So you prepare the die, and then you start to vacuum laminations. You beat up the resins, and you cure it, and you drill holes with the lasers, and then you plated it using electroless plating. You're not going to use a typical ECD we discussed in the silicon interposer. This is electroless, and then you do all kinds of patterning again, and then you do this one. You do electro copper plating. So you could do all kinds of stuff in the here, and then so you repeat it. So you could generate these layers very nicely. So you can see that that's the reason it's highly. That's what we mentioned in the early one. That this this one has the very high flexibility in attaching dies. So that's the beauty of this material. And that's the reason they could make so many layers of packaging, routing, and all that to make it happen. And I think that's the reason, one of the reasons I would say that is the success of Elia company. Then, so this is another one. They could tune right? So they could also adjust everything they need. If you want an antenna structure, you need the low dielectric loss. You need to change the physical thickness. You could all do that. We'll go do that. As if this material is kind of a user friendly. Right? And what I meant is that you could tune it. OI can be tuned to fit because it contains all kinds of materials, right? And this one is just example, comparing all kinds of organic materials, their curing temperature, their dielectric constant, their D value, decay value, displacing factors, and then the coefficient of thermal expansion, and then mechanical strengths. This one is kind of now it's kind of weak, right? The megapascal. Remember, silicon is gigapascal, it's quarters of a measure higher. Just give you a reference. And it could bend allocations, right? It's the rigidity is a problem. The residual stress is small, okay? And then the moisture uptake, they like to absorb moisture, and that's could be a problem. Remember, when we talk about glass interposer last time in the last talk, the moisture uptake by the glass is zero, and here you got some percent, and this give me worried because if you look at this, if you have organic interposer here, and then you have a high moisture absorption, is that going to give you a problem? I don't know, but usually any organic material like plastics, you put water there or long and high temperature water there, usually the plastic will be in trouble. Unless you change the chemistry a lot in a way so that it's water compatible, high temperature water compatible, then organic interposer is not going to be happy in this environment. Okay. Of course, they all can be tuned, right? In theory, they all can be tuned. Now, that BCB has the best dielectric constant. Okay, the BCB, then it has the best dielectric constant 2.61, but suffer from high thermal coefficient, 70. That's not good, right? These are as small as possible. Polyimide, epoxy, okay, PBO, all these different organic material. I think they are the tools in the toolbox of Ajinomoto. Yeah, Ajinomoto can tune it, right? That this one, the ABF, right now, that what we just show uh, in the TSMC OPOR, it's SPT is GO 102, and now they have something better. Okay, so they're improving pretty much. They're improving. Okay, so maybe one of these days is a perfect plastic material, organic material that could be as good as silicon. I think that would be the dream at the cost to ornamental lower, right? So the bottom line is this table I'd like to summarize for you. Can the extendability and scalability OI eat silicon interposers lunch? Silicon interposer, very high interconnect density, high specific capacitance density, and large radical size. It can do the visual large radical size. But all I can do is getting there, right? It could do large radical size, and then it's very high, getting approaching the silicon interconnect densities, and then the capacitance, not so, but no. In theory, you could tune it, right? And then so the I the point is that you could hopefully you could break into all these market segments in a way by tuning your OI materials, but it has to be HVN compatible, right? And then in that sense, potentially you could eat silicon interposer's lunch. The final concern I have is probably this, and I think this is probably the most worrisome. When you go scale more and more, silicon still stands rigid and good. So water flowing inside and out, no problem. And then when I react with water, if you add the water with some small additive, so as that you will not attack the silicon uh, this material, then you're fine. It's been demonstrated already, right? But nobody has tried to do that with OI. That probably is my last concern about OI. Okay. So, hey, folks, this is conclude my talk. Will organic interposer eat silicon interposer's lunch? Maybe, maybe. That will be the dream of the alliance using a cheap organic substrate and then avoid silicon interposer altogether from the get-go, or the ABF Ajinomoto's material that improve the material in a way that could keep encroaching on silicon interposers once table. And now I will show you a trick with Ben. I hope you enjoyed it. Yeah, that concludes my talk. Thank you very much.